The last video explained how this equation takes its form. Now let's talk about some of the details. First of all, what does potential energy represent? It's very important to understand that potential energy represents the transfer of energy within the system. Energy transfer within the system. When two objects interact, like the Earth and a box, there's stored energy when the box is up high in the gravitational field. When we release it, the box moves down lower, and that energy is transferred to the box as kinetic energy. The potential energy is just a way of telling us how the Earth and the box are going to interact and how the energy is going to be transferred. The most important thing here is understanding what our system is and what is external to our system. If things are internal to the system and they interact with each other, we often account for energy transfer with potential energy terms. If they're external to the system, we do not use potential energy, we use work done by external forces. So let's take this example with the block and the Earth. Let's call this case 1, the Earth, our block, mass m, at some height h. And what I'm going to do is pick my system to include the Earth, the block and the Earth. So when I write my energy equation, I account for the fact that the mass is in the gravitational field of the Earth with a potential energy term. So I would say, let's pretend our mass starts off at rest, and we want to know what is V final just before it hits the ground. So let's use this energy equation. The initial kinetic energy is 0, because our initial velocity is 0. We're going to have some gravitational potential energy, either at the beginning or the end. Let's wait on that one. Springs. Do we have any springs in our system? No. So they don't store any energy, not at the beginning and not at the end. They don't exist. Are there any external forces reaching into our system? No, because our system is pretty big. It includes the force of gravity, so we're good. No external forces. And there's no friction, and we're going to ignore air resistance. Our gravitational potential energy is fairly arbitrary. We need to define a 0 for our height, and it makes sense to choose either the starting position or the ending position. Most people like the lowest point in the problem to be the 0 for gravitational potential energy, so I'm going to make my final 0, which means at the beginning I have mgh worth of gravitational potential energy, and everything else is 0, so that's my initial energy. And at the end, the only thing I'm left with is kinetic energy, 1/2 m V final squared. The mass cancels, and I get V final is the square root of 2gh. Now let's take a look at the exact same problem. Here's our mass. There's the Earth. This time, I'm going to define the system this way, not including the Earth. So it's the same question. If it starts at a height h, how fast is it going right before it hits the ground, released from rest? If my system does not include the Earth, then I cannot have a gravitational potential energy, because this is only for internal interactions within my system. So I have no gravitational energy. I have no springs in my system, so I'll just cross those off. What I have is work done by an external force. I have the Earth reaching into my system and exerting a force. So the force of gravity multiplied by the distance is the work done by gravity. I have no friction or air resistance, and I have a final kinetic energy. So what I end up with, the force of gravity is mg, the distance is h, so the work done by my external force, the work done by gravity, is mgh, and it's positive because the force is down and the displacement is down. The box is moving in the downward direction. And I get V final is the square root of 2gh. The same thing I got earlier, because there's two ways of viewing this. You can define the Earth as part of your system, and then you have to use the gravitational potential energy to account for the interactions of the two objects within the system. Or you do not include the Earth. You view gravity as an external force, and then you eliminate potential energy terms because the Earth's not part of our system. We can't have gravitational potential energy. What we have is an external force acting on our system. Let me do another example, this time with a spring. So we have a spring sitting here. The box has some initial velocity, and we want to know how far does the spring compress before the block comes to rest. So that's the problem. The box is sliding in. Let's make our surface frictionless. The block is sliding in on a frictionless surface. It encounters a spring, and it starts to compress the spring, comes to rest at some position. We're trying to figure out where it comes to rest. How much is the spring compressed when our box comes to rest? There's our equation. Let's start filling in what we know. In this case, I'm going to include the spring in my system. So I'm going to pick a different color here to define my system. How about red? So I'm going to define my system as including the spring. Do I have initial kinetic energy? Yes, 1/2 mv initial squared. Gravitational potential energy. We can pick any place to be 0. Let's pick this height to be 0 height, which means that we're not going to have any gravitational potential energy at the beginning or at the end because it has the same height at both places. Spring potential energy. At the beginning, we have none. Now we have to include spring potential energy now because the spring is part of our system, and this is how we account for internal interactions. But at the beginning, we don't have any. The spring is not stretched or compressed. Do we have any external forces acting on our system? No, we don't. Is there any friction? No. So our initial energy is just the energy of motion, the kinetic energy of the block. Kinetic energy of the block. And at the end, it's not moving, so there's no kinetic energy, but there is spring energy. 1/2 k x squared, the distance the spring has compressed. Remember, spring potential energy, always a positive number. 1/2 kx squared, it can't be negative. Doesn't matter whether the spring is stretched or compressed, it has the same amount of energy stored in it, and it's always a positive quantity. Okay, so we solve this for the x value, and we get the square root of m/k times v initial. Now let's do the exact same problem again, but this time that's going to be our system. No spring. Here's our equation. Let's see what we've got now. Kinetic energy, initial kinetic energy, absolutely, 1/2 mv initial squared. The block is moving initially. Gravitational potential energy, I'm going to say it's 0 at the beginning, and at the end it's at the same height, so it's 0 at the end. I do not have a spring in my system, so I'm going to drop the spring potential energy terms. But I have an external force, something reaching into my system, doing work on it. It's the spring. So I've got here plus the work done by the spring. And there's no friction. Is my block moving at the end? No, it's not. So those have to add to 0. So the question is, what is the work done by the spring? Remember, work done by the spring, I'm going to come off over here on the side, is plus or minus 1/2 kx squared. So earlier I told you that the energy stored in a spring, the potential energy of a spring, is always positive, 1/2 kx squared. But the work done by a spring on an object could be positive or negative. So don't mix that up. Here we have the work done by the spring on the block. And in this case, it's doing negative work, and the value is 1/2 kx squared, work done by a spring. Why is it negative? Because the block is sliding to the left, but the force of the spring on the block is to the right. It's slowing the block down, doing negative work on the block. And what do I get? I move that to the other side, and I have the exact same equation. So you can view things as being part of the system. If they're part of the system, you use gravitational or spring potential energies to account for the springs and the Earth's influence on our system. Or you view those objects as being external to the system, and you use work done by the external force in this equation. But don't do both. Don't double count the effect of a spring or the effect of gravity by including both in your calculation. So most people prefer using energy conservation to solve this type of problem. In your previous chapter, you probably saw how you can solve these problems just looking at the work done by every single force acting on an object, and you said the net work done was equal to the change in kinetic energy, and that worked pretty well. But it becomes kind of tedious, especially as your systems become a little more complex, multiple objects, and springs and gravity and all kinds of forces interacting. Typically, it's a little more straightforward just to use energy conservation. Why don't we look at the same situation we had previously, but let's add friction. The block is sliding to the left. Right when it gets to this point, it has a speed v initial. That's x equals 0. And we want to know how far it compresses the spring when it comes to rest. So the initial speed is the speed of the block just as it's making contact with the spring. And the spring is in its unstretched length. And of course now we have friction. So we have to use some coefficient of friction in solving this problem. It's not going to slide as far in this case as it did in this example earlier, because there's friction now also dissipating some of that mechanical energy into heat. Let's start with our equation and let's see what we've got. How are we going to define our system? I say let's include the spring in our system. I like that. So our system is going to include everything, the Earth and the block and the spring. Do we have initial kinetic energy? Absolutely. The block is moving with speed v initial, so that's 1/2 mv initial squared. Gravitational potential energy, I'm going to say it's 0 at this height, and it never changes in height, so the final is also going to be 0. Spring potential energy, we have to use spring potential energy because the spring is internal to our system. At the beginning it is unstretched, so it has no energy stored in it, but at the end it does have energy stored. It's compressed, so we need to account for that. Do we have any external forces acting on our system? No, we don't. But we do have friction. And what is the work done by friction? It's going to be the force of friction, which is, I'm just going to write F sub k, multiplied by the distance, which we're calling x in this case. And there's a cosine of 180, so I'm going to put a minus sign right there. The friction is going to the right, the box is moving to the left, so it's negative. the friction force times the distance. So this number is negative, and that's why it's on the left-hand side of the equation. Is our block moving at the end? No, it's not. But we do have energy at the end in our spring, 1/2 k x squared, and we're solving for x. So we'll move some of these. Oh, first of all, what is friction force? Friction force is mu, the coefficient of kinetic friction, times the normal force, which is mg, and the distance here is x. So we can move everything to the other side, and then we have a quadratic equation. So we have a quadratic equation here. Why don't I give you numbers for k, mu, m, and v initial, and let's solve this. So why don't we say that our mass is 2 kilograms. The coefficient of kinetic friction is 0.3. The spring constant is 50 newtons per meter. And the initial speed of our object, the initial velocity, is 20 meters per second. So using my quadratic equation, I get x is 3.88 meters. Let's take a look what we would have gotten earlier. Should be a little bit more than that. And it looks like the distance would have been 5.66 meters without friction. With friction, 3.88 meters. So the numbers appear to make sense. Hopefully that'll give you an idea of how to use these equations. The important thing is defining your system and understanding which forces are internal to the system, in which case we would use potential energy terms to account for the energy transfers, or external to the system, in which case we use the work done by external forces.